We continue with the previous section. Now is section 2. In the last section, we have seen the dose calibrator and its schematic diagram. So the principles of operation is quite obvious. When there is no radioactivity present, there is no electrical current flowing between the electrodes. And as soon as a vial or syringe containing radiopharmaceutical is put into the chamber, and it ionizes the gas molecules, and it results in producing the signals and the readouts of the radioactivity level. Okay, so these are a continuation of the principle of operation. Please read. And in the last paragraph, you see that the readout could be given either in millicuries or in megabecquerel. Just to recap, remember that the degree to which ionization occurs is not only a function of the amount of radionuclide, but it is also a function of the energy level. And for example, if you're talking about technetium-99m, its energy emitted is 140 keV, whereas the gamma energy that's emitted by iodine-131 is 364 keV. So therefore a correction factor is necessary so that the calibrator reads the same for all activities that are equal. In other words, a certain adjustable mechanism is needed, and those results in the having different types of buttons which are used for each of the individual radionuclides or to be measured. So you will have technetium-99m button, you have iodine-131 and other radionuclide buttons to complete the functionality of the dose calibrator. So how do you use a dose calibrator? It's quite simple. And first things first, you have to select the radionuclide button, place the syringe or the vial containing radiopharmaceutical right inside the chamber using the device that is given by the manufacturer for you to lower the radiopharmaceutical vial or syringe right to the bottom of the well chamber, and the appropriate reading will be displayed either in curies or megabecquerel depending on the preference of your department. So for some extra and required study as your homework, and please check how you would calibrate a dose calibrator. Hopefully we can discuss this in our meeting tomorrow or in the next meeting that we're going to have another session, inshallah. And another task that I'm giving you is how would you measure molybdenum breakthrough or contaminant in the technetium-99m solution. For those of you in the future, we are going to have a lecture on generator system. So one of the generator system that are commonly used in the nuclear medicine department is a technetium-99m generator. The parent radionuclide is molybdenum-99, which decays into Tc-99m, and you have to make sure that for every elution of the generator for Tc-99m, there should not be considerable presence of molybdenum-99. So for that, you need to conduct what is termed as molybdenum-99 breakthrough. So we discuss this in our meeting, and either tomorrow or in our next meeting. How is that conducted? So the first one is how do you calibrate a dose calibrator? What are the various terms of calibration being used, and how do you do the calibration? Number two, how do you conduct molybdenum-99 breakthrough? Now we come to the other counter which uses gas field, which is the Geiger-Müller counter. So Geiger-Müller counter is another example of gas field counters which can be used for measuring alpha, beta and gamma radiation. If you notice that at the very last point, in order for you to detect beta radiation, the detector must be equipped with a sufficiently thin window. So why do we need a thin window in order to measure beta radiation? So we can raise in our discussion tomorrow, inshallah. And so for the GM counters, it operates as a rate meter, meaning to say the readout will be micro Roentgen per hour or milli Roentgen per hour. GM counters does not have energy discriminative capabilities like the one that we have just discussed with dose calibrator, and it takes into account the energy, and so you have the various buttons for you to detect technetium, iodine 131 and so forth. But for GM counters, they do not have energy discriminative capabilities, so any radiation would trigger the ionization of the gas chamber, and you will get the readout in micro Roentgen per hour or MR per hour or CPM, even counts per minute. Right? So GM counters are usually used for contamination of low level activities. For high level activities it's not useful. We will see in the next slide why it is not usable for high level radioactivity. And like those calibrator, if you need to calibrate, GM counters also is required to be calibrated using standard sources according to the SOP requirement for its proper usage. So this is an extension of how GM counter operates. So I hope you will read through this slide, but I wish to share with you the last paragraph of the GM counter. The problem with GM counters is that above a certain level of gamma or beta radiation, and it leads to what is known as the desaturation of the GM tube, meaning to say the radiation detection will drop to zero, even though there is radioactivity, but since the radioactivity is too high, the GM will become saturated and the readout will just show zero. So this is a limitation of GM counter. That's the reason why we mentioned that GM counter is used for low level radiation, not for high level. Okay, and the other limitation is GM counters, you cannot use it for measuring tritium, because tritium is having a very low energy emission of 18 keV from its nuclide. Beta particle, 18 keV beta particle, which is considered to be weak beta, and GM counters are not useful for its measurement. And so when you have gamma contamination, it is best actually if you scan, you survey using scintillation detectors rather than GM detectors.